All right, it's day 95 of 100 Days of ML, and I'm going to be learning about semi-supervised learning in today's session. First off, I'm going to start off with this article about DeepMind's new supermodel. I have no idea what it is, but it's going to be an interesting read. Then I'm going to proceed by reading about code training and semi-supervised learning. It's probably just going to read a small article on semi-supervised learning, get an understanding of what it is, and then proceed by going into code training. Reading this article, where is it? There's a couple of papers that I need to read. It's this one. Pseudo-labeling of offensive content classification. A couple more. So we'll start off with first thing, this artificial intelligence blog post by Jesse Rodriguez. Transformer that can handle any data set. Process audio, video, and images using a single model. So what it looks like is this model perceiver. There's two of them actually. The first one was a more general model, but before getting into that, the introduction is the fact that the existing models, deep learning models, currently process only one type of data, whether it's text, video, audio. It's specialized for one given task and one given type of data set. And this constraint is not optimal because of the fact that, when you look at humans, we're able to have a combination of all of these types of inputs. And that's sort of where multimodal training comes from too. And I want to read up on that as well. Multimodal. deep learning. I'll search that up in the next. So it's similar to that, I guess. I'm not sure what the difference is between multimodal and this perceiver, where it's a general perception with iterative attention. So this first perceiver, I'll call this version 1, was able to process different types of inputs like images, point clouds, audio, video, and their combinations, making it a multimodal model. But it was only limited to classification. And so this next model, Perceiver IO, I'll call this version 2, is now able to also it's able to do what it was able to do in version 1, but in addition to that, it's able to be applied for more complex multimodal tasks like computer games. So I think this is, in fact, a multimodal model. And a lot of the research that has been coming out in the past year, or maybe even less than a year, has been under multimodal learning. So it's interesting to see like where this is going to go. So they're both built on transformer architectures. Looks like the attention model encodes the input into smaller latent arrays. Processing cost is independent. Size of the input. It's able to scale gracefully. I think Google blog had something about multimodal. No, this is not what I'm looking for. Okay, this might be it. I need to subscribe to this feed. But how do I subscribe? So multimodal has a small number of modularity-specific subnetworks for audio, images, or text, and a shared model consisting of an encoder, input-output, mixer, and decoder. Shared model consisting of encoder, input-output, mixer, and decoder. So I guess these could be the specifications of what type of input it is, whether it's audio, images, or text. So this would be the subnetwork, which is connected to the encoder, the mixer, and the decoder, which is all just a shared model. able to detect objects and images, provide captions, recognize speech, and translate between 4 pairs of language. And do, oh my gosh, that's a lot of things. It's part of the tensor to tensor library. Interesting. I have to give this a paper a read probably tomorrow. How do I subscribe to the Google AI blog? There's something at the bottom. Content updates in Yahoo, NewsGator, Bloglines, and other news readers. I mean, I just want an email notification every time something's posted. I don't know about this. Okay, now let's move on to semi-supervised learning. I explored this a little bit in one of the textbooks that I was reading, where it was talking about different types of learning, supervised, semi-supervised, and unsupervised learning. So I have a brief explanation in my mind, but let's try to get something more rigid. Transduction versus induction. Transduce is to convert something into another form. Books on semi-supervised learning. Summary, okay. Geeks for Geeks. Not the best to check out for this Medium article. We can easily protrude a neural image classifier by adding some noise to the input image. This noise could be small so that we could detect it with the naked eye through the neural classifier, though the neural classifier can. Oh, we can't detect it, but the neural classifier can. Deliberately try to introduce noise that will maximize the failure of the classifier, prompting it to incorrectly identify a given image. Don't use labels for a training set, but rather the conditional probability that an image will have label X. Okay, so it predicts the probability of what object it could probably be. So 40% panda, 20% bird, 1% car, and so on. So it's some sort of distribution where I think the distribution adds up to 100% probability. I forgot what it is, probably like a sigmoid or something. We could still tell the classifier that the correct label is blah, blah, blah. This allows us to do semi-supervised learning. So that distribution itself becomes the label during the adversarial training. So I guess we use the unsupervised learning part to predict what probability it is of which object it is, and use that distribution for training, for adversarial training. Hmm. So the adversarial method tries to make the model fail the most. And in this case, the model tries to make perturbations to the images that maximize the divergence between the predicted label and the correct label distribution. Predicted p-label features for unlabeled images. The perturbation would be the maximum perturbation of what's KL? Kullback labor labeler divergence divided by KL. And we also have features plus perturbations. This is the one with the noise. And whichever has the most amount of perturbation, we take the maximum for that and then we assign it into perturbation. Then we try to minimize the loss for that. Okay, nice. Pretty cool. Regularization method for supervised semi-supervised learning. Okay, let's check out some other things. Our feature space X and our label Y. Construct a predictor such that we're mapping the feature space to the label, and we try to minimize R of F, where this is a loss function, estimator of xy loss y, comma f of x, where f of x is a predictor. So we're trying to minimize the error between the actual prediction made by the predictor and the actual label, and we're using an estimator function for x and y to get the minimum. Learn a good prediction rule from the training data. Labeled. This is supervised learning, where we're trying to predict the label data. And semi-supervised learning, so we have the labeled data and unlabeled data. So x of I, y of I has to be equal to 1. And for unlabeled data, we only have the predictions that are made from using the predictor function. And we have no label space, no y. Here m is greater than n. So the amount of unlabeled data is actually greater than the amount of labeled data by a lot. Get a better prediction rule than based on label data alone. Learn a better prediction rule than based on label data alone. Okay. So these are some of the semi-supervised learning algorithms, and this is what I'm going to be looking into: code training. So there's self-training, generative models, graph-based methods, semi-supervised SVM, and others. Okay, this is self-training. Mixture models. This is the code training. Code training. I have a feature split X, which is X1, X2 exists. X1 view, X2 view. Okay, sure. X1 or X2 alone is sufficient to train a good classifier. I think X1 and X2 is just the meaning that at least two different features exists. Like like a cat and a dog or something like that. It's alone to train a good classifier. Co-training Blum and Mitchell, 1998. Mitchell, 1999. Features can be split into two sets. Each subfeature is sufficient to train a good classifier. Those are the assumptions made. Two separate classifiers are trained with the labeled data on the two subfeature sets, respectively. Two separate classifiers are trained with labeled data on the two subfeature sets, respectively. Okay, so two separate classifiers are trained on X1 and X2. Each classifier then classifies unlabeled data and teaches the other classifiers with a few unlabeled examples and the predicted labels. They feel the most confident. Okay, so we have two sets of classifiers, X1, X2. X1, they both learn on, they both learn separately on labeled data. And then each one tries to classify unlabeled data, and they share the answers between each other, especially if one has a higher confidence on the prediction. It teaches the other classifier that this is what's right, this is what's wrong, and probably back propagation happens in the other classifier if it's a deep learning model. Otherwise, if it's a regular model, that process of learning would be a little different. Each classifier is retrained with additional training examples given by other classifier. The process repeats. So this is the co-training algorithm introduced by Blum and Mitchell. We have input labeled data, L, so X of I, Y, Y. So here we have the label space. In unlabeled data, we don't have the label space, and it's usually greater than the amount of labeled data we have. So that's why we have an L plus U. And our J starts from L plus 1. Each instance has two views, so x1, xi of 1, xi of 2, and the learning speed k. L1 is equal to L2 is equal to x. So we have a sequence of a set of labeled data points here, which is L1 and L2. Initially, what the classifiers are getting inputted. Repeat until unlabeled data is used up. Okay. Train view minus 1, f of 1 from L of 1. F of 1 should be x of 1. So it's the first prediction used during unlabeled data from L of 1, and view 2, f of 2 from L2. So this is where I guess the two views come into play, v1, v2, x1, x2. What does it mean to have two different views? I mean, I get this part, but I still don't understand the differences here. View 1, view 2. I don't know. Something I should consider looking into again. Classify unlabeled data with ff1, ff2 separately. Add ff1's top k most confident predictions to L2. Add ff2 tops k most confidence predictions where k is the learning speed to L1, and remove these from the unlabeled data. So this is the training part where the k most predictions in the other classifier gets added into the alternate classifier. I think there's an implementation of this on GitHub. Let me pull that up. How do I zoom in? What's NP? Number of negative examples that will be labeled. Number of positive examples that will be labeled by each classifier during each iteration. Default is determined by the smallest integer ratio. Samples in L. Positive to negative and negative to positive. No, are these both the same thing? Well, one's positive examples and one's negative examples. I don't know. Well, K is the learning rate. I know that. And the learning speed, which is introduced in this right here. I'm not sure what N and P are. U, size of the pool of unlabeled samples. Let's classify and partially labeled data. -1 indicates unlabeled. So if it's -1, we have to do the unlabeled training. y is equal to np dot as array y complex slicing. Wait, no, this is not. Set the n and p parameters if we need it to. Okay, so if it wasn't assigned already, we can do it right now. So assert that all of these are greater than 0. Unlabeled samples. Samples are initially labeled. U prime is probably the top k confident labels from the previous predictions, and we remove that from U. I'm not too sure about that because the loop hasn't even started yet. These are just initializations. And now we train here, loop until we have assigned labels to everything in U, hit iteration break condition. A lot of things going on here. So fit in, okay, so we have two classifiers, CLF1 and CLF2 here. They're both trying to predict on the label data using L as our increment. Where's L? Over here. And then we have Y1, Y2 based on the probability distribution. So this is f of x. And so now we have our supervised training and unsupervised training distributions. NP empty sets. And I think what's going on here is picking the top k confident predictions. Label the samples and remove the newly added samples from U dash. So this is positive. Was it positive examples that will be labeled? These are negative examples. Okay, I think I understand. Okay, so the positive, basically, okay, how do I say this? So we have a learning speed of k, and this is a classification model. So either the classification is going to be 0 or 1 based on, due to the fact that we essentially just have two hold on, I'm getting a call. Okay, anyway, so this is a classification, so it has to be a 0 or 1. And so the top k could either be a positive or a negative prediction, right? So in order to introduce that, what we do is we take the top k positive and top k negative. And so we assign the most confident positives and negatives to 1 and 0 respectively. to the unlabeled samples, and we remove that from the unlabeled list. Then we add new elements to U dash. Not too sure what this is here. And we can fit our final model. After introducing the labeled data of unlabeled data into the regular labeled pool, we could refit again. And we have a prediction here. Okay, cool. I mean, I don't fully understand it, but I think I understand something. Probably gonna call the stream here. Update GitHub and come back tomorrow. So today was semi-supervised learning. Started with this article. Next, we looked at multimodal models. Next up, we checked out semi-supervised learning models. Code training algorithm. That'll link this. All right, that's pretty much it for today. I'll have to figure out what I'm going to do tomorrow. So I'm just doing day 96. You'll probably go back to deep learning or take a look at adversarial learning. Maybe that's an option as well, or go more in depth into multimodal. So I'll write multimodal for now, and we'll pick what we want to do. Tomorrow. Okay, finish day 95. That's it.